Hello, hopefully you can hear me. There are some changes in software I'm using to do this screencasts, and I'm not sure if the microphone is working. So let's just hope that it does. I will be doing this education round. Yeah, I should probably switch to English. Okay, so we have some queries. Each query is 2 strings, and we should check if in the second string there is a substring such that it is some permutation of a string. Those lengths are up to 100. So I think the easy solution is just to try all the substrings, but not all of them. We know that the length should remain the same, so we will try all the substrings of second one such that the length is exactly the same as it were, and then we should check if it can be a permutation of our first string. To do this, we should just check if they're like equal as multisets, and it's the same as if we will sort both of them, will they be equal or not? So the complexity of the solution for one query is we should check all of m possibilities, and each of them will be checked in n-log n time due to sorting. So the total complexity is the product of lengths times log n, so it's 100 times 100 times 100 times log, which is fine. For the first string, we can do sorting just one time. I have to copy my substring to another string because I don't want to ruin my initial string. It can we have to start to do all the checks independently. Yeah, I decided that I want to return the values, so this should be terminal, and we should print the answer. Okay, we have two numbers A and B. We can do some operations, and in case of these operations, we increase one of these numbers by k. So in first operation, we increase by 1, second by 2, and so on. And we want to make these numbers equal, and we want to know the minimal number of operations to do that. So it's obvious that we only care about the difference of these numbers, so we actually have one number. We can increase or decrease it, and like we should get 0 at the end. Okay, so basically, if we do k of don't use k, n operations, like for each operation we should choose do we want it to go with plus sign or with minus. And we want to split all the operations into parts such that the difference is exactly a minus b. So what should we know? Like it's clear that we can change the parity of the difference. Like if we take one operation and change it from plus to minus, it changes the balance by 2 times the number of, from this operation. So we cannot change the parity. So if the parity is wrong, we cannot do anything. But all other things are fine. Like it's obvious that we cannot get difference more than like sum of all operations, but everything between minus sum and plus sum with the same parity is reachable. It's kind of easy to see. Like we can just if we want some fixed difference which between minus sum and plus sum and have correct parity, we can calculate how many like how much sum should be in one part and just take it greedily from the end. I mean, if we can take n, let's do this. If we can't, let's not, and go from n to 1. It's easy to see that we will actually get the sum we want. So we only have to worry about getting big enough sum and getting correct parity. For the parity reason, you can't actually use binary search. You can solve this problem in like O of 1 time, but like O of square root is enough. Like answer will be O of square root of the difference. So you can just increase the answer by 1 every time and check if everything is good. Like the sum is big enough and the parity is parity you want. But let's do this in constant time, because why not? It's kind of interesting. Like, the idea is just if there wouldn't be any restrictions in parity, you could do it in binary search or in constant time just by calculating some formula, like the sum of numbers from 1 to n is n times n plus 1 divided by 4 or by 2. So yeah, we can find the smallest number is such that the sum is at least balance. And then, like, starting from this number, we will just go like increasing by 1, like in square root solution, and we will reach the answer in constant number of iterations, because like parity changes every 2 steps. Like each time when you got new odd numbers, parity will change. So we will have to do no more than 2 steps. Okay, let's do this. Yeah, we care only about absolute value. We can multiply everything by -1 if you want to. So we want to find the smallest number such that n times n plus 1 divided by 2 is at least x. So we can instead do n times n plus 1 2x. And let's just say that we can take square root of 2 times x and just subtract something such as we will get smaller number and then go one by one. We can just say something like this. So what I'm doing here, I'm just saying that like we could solve this quadratic equation, but we don't need to. The solution is somewhere close to square root of 2 times x. So we just calculate this, then do this while to decrease if we overdo it. So n can be slightly bigger than actual number, so we will decrease it while it's not, and then this is just checking if n is correct answer now, and if it's not, we will check the next one. So I can like delete this to these 2 lines and get solution in square root time, and with these 2 lines it should be constant time. Oh, cool. So Yes, there can be some problems if x is 0. I don't know why there would be. So x is 0, so this should be 0. Oh, okay. This is not the correct way to. So we should just say when the n is strictly positive in this n minus 1. So n is at least 0. Let's just check. So n is at least 0, and we could just do this x. So yeah. Okay, we have two sequences of numbers 1 and 2. They're of equal length n. We can delete the suffix of first sequence and prefix of second sequence, and we want the remaining number of ones and twos to become equal. We can reverse, for example, the second one, so we always delete suffixes. And we want to erase the minimal number of elements. Okay, yeah. We can see that there will be the remaining part will be prefixes, and if we calculate the balances on each prefix, like what should balances on the prefix on each prefix will be if it's valid solution. Like the sum should be 0, obviously. It's the definition of their equal amount of ones and twos. Balance is like the number of ones minus the number of twos, for example. So yeah, we can try all the prefixes of first sequence. And like now we know the balance for this prefix. So in the second sequence, we want to choose the longest prefix with such a balance that their sum will be 0. So we know what prefix we want. So we have to somehow answer queries like what is the longest prefix with given balance. To do this, we can just pre-calculate all the answers, like calculate balances for all prefixes of the second sequence, and for each balance, just remember what was the longest one. So the whole solution is will work in linear time. let's not forget to reverse the second sequence. So, what can our balances be? We start from 0 and we go through n elements, so the balances will be from minus n to n. But negative balances are not very convenient because we want to store something for them, so we want to use balance as a array index. So to solve this problem, we'll just add some fixed amount to all the balances. For example, we could add n, so all the balances will be from 0 to 2 times n, and now we want to say that at first there are no such balances, and for example the answer is -1, and if we see -1, it means that there is no such prefix with that fixed balance. Okay. So we start with balance n, not 0, because we want all the balances shifted. We could say like maximum because we want the longest prefix, but it's actually will be maximum because we are going through prefixes from left to right. And yeah, we shouldn't forget about the whole prefix, but we shouldn't do anything with the nth element. We should change the balance. So if we encounter 1, it's +1, and if we encounter 2, it's -1. Okay. So ans is the sum of two longest prefixes, not the best answer, the maximum number of numbers we can left. I could like set -1 here, but 0, 0 is always a good answer, so let's say that answer is 0 initially. Balance is, could say -1. Just that the sum is still 0. We want to take answer from minus balance. That's the balance that will get the sum to 0. And if it's not -1, so such prefix exists, then we will update the answer with value what I plus current. So I is the length of prefix in first array, and car is the maximum prefix with given balance in the second. And again, if we reach the end, we stop and we change the balance. And I think that we actually need to print the number of elements we erase. Unused, yeah, because this should be up to 2n. Yeah, should be 8. So we have some segments on a line. It's guaranteed that none of all of the endpoints are distinct, and it looks like they're permutation of numbers from 1 to n. And we want to build a graph. These segments are the vertices, and we have an edge between two vertices if the segments are intersecting, and if they're not intersecting, we don't have an edge. And we want to check if the graph is a tree. I want to say that the graph of this kind is a tree if and don't leave. It is like every graph is a tree if and don't leave it is connected and don't have cycles. To check if it is connected, we should check if we can divide these segments into two parts that there are no edges between them. And to do that, like this division exists. Even if and don't leave, we can divide the segments on into left and right part. So there's okay. Let's do some drawing. This looks like a good problem for some drawing. So we have a line. We have some segments. So we want to check if it is connected. And no cycles. So the first part, checking if it is connected. I want to say that we should just check if there is no way to choose some point such that there are some segments on the left and some segments on the right, but nothing contains this sixth spot. Like, if such thing exists, it's obvious that the graph is not connected. We cannot go from this part to this part. But like, if there is no such thing, I state that like everything is connected actually, because like, we could start from what to say. Like, let's look at some connected component of the graph. It shouldn't be all of the segments. So let's say that there are some segments which are connected component. Some segments. They form connected components, so nothing intersect the segment, nothing from outside this connected component. Let's look at the union of these segments. It's one big segment. Why is that? Like, union of any number of segments is union of non-intersecting segments, and if we have two non-intersecting segments, then like obviously the segment from one part is not connected to the segment in other part. So let's look at some other segments. I state that actually like this is this division and this division. It can happen that there are no segments here, but if there are also no segments here, like then this connected component can have all segments. Like, how can a segment look like if it's not intersected any of this? So it's not intersecting the union. So it's either on the left or on the right. So basically, all of the segments should be either strictly on the left or strictly on the right. So it means that both of these lines are borders. So to check this, we should check if no borders exist. And to check if there are no cycles, like I want to say that if there is a cycle, then there is a cycle of length 3, so it's click on 3 vertices. Why is that? Okay, let's look at some cycle. So it's something. You know what cycle is, right? So let's look at the leftmost, for example, by right end. So let's choose the segment, like one of the vertices, which has the leftmost right end of the segment. Let's say that it is this one. So it's some segment. And for all these vertices, the right endpoint is somewhere to the right. So here, somewhere. Okay, then let's look at these two vertices. So let's say that this is this right endpoint and this one has this right endpoint, for example. They should intersect with this segment because there is an edge. So it should look something like this. But then I state that all these 3 segments have intersection, like this point. I mean, these 2 segments also intersect because they have like the rightmost part of this segment. So it's actually a cycle of length 3. How to check if this thing exists? Like there should be a some part which is in 3 different segments. For example, we can just for each like segment of length 1 calculate if it is covered by at least 3 segments, and we actually can calculate if it is like by how many segments it is covered. So whole solution covered by 3 segments. We have these segments. Let's say that we have like segments of length 1 and the things between them. Like we can just multiply everything by 2 and say that I want to like, add some points in between the segments of length 1. So if we have like these 2 segments, I want to say something about this part. How to do this? Like, yeah, we should multiply everything by 2, and I want to say like probably yeah, probably we shouldn't do anything more. Just multiply everything by 2, and like the points with even coordinates will be like these things, and the points with odd coordinates will be the points between the segments. So to check this, we want to check if all the sums in even coordinates are no more than 2. And to check this, we want to check that all the things between segments are covered, so there at least one. And to calculate the sums, we will just use prefix sums. We don't need any data structures advanced. Like we care only about the finished results, so we can use prefix sums. We want to multiply everything by 2, and coordinates at first are also multiplied by 2, like they're from 1 to 2 times n. So our array should be of length 2 million. Very We should be careful about what are the borders. Let's not subtract anything, we just think about it later. So I want everything from Alt to R inclusive be in a second, so I'll do this. So now I'm just calculating prefix sums. Now I want to check if everything is good. So my segments of length 1, they were numbered from 1 to 2 times n, so now they're from 2 times 4 times, from 2 to 4 times n, and so if we have more than 2, then we have a cycle of length 3, which is bad. And the things between them, well, obviously they should be bigger than 2 and smaller than 4 times n, so and they're all good. If some of them is 0, then the graph is not connected. And otherwise everything is good. Yeah. Okay, so what we have calculated. Oh, I read the problem wrong. Cool. So there is an edge if okay. So they intersect, and neither of it lies fully inside the other one. So okay, they form an inversion. Okay. So if we have this, it's not an edge. It's an edge only if it's something like this. So they not form an inversion. Okay. also not right. Okay, all of this is wrong, I guess. And yeah, it can happen that there are cycles of length more than 3. For example, this thing, this connected, this connected, this connected, this connected, and there is no edge here and no edge here because this lies inside of this. Okay, I guess we can just build the graph and check if it's true. Like using that, if we draw many edges, more than n-1, then it's definitely not a tree. How do we do this? Let's go from left to right, and we will store in some array all the segments that are opened now, that have started but have not finished yet. So we have some segments. When we encounter the beginning of new segment, we just add it to the end of our array. The array is sorted by the, like, in order we encountered all of this. What will happen when we find the end? We should draw all the edges that the segment have, which is not already drawn. Like our variant is that for all the segments which are fully to the left, like they have ended, for example, if I'm staying here, this segment fully ended. For this segment, we already have drawn all the edges, and when we encounter the endpoint, we should draw all the edges to the segments that are not fully ended yet. So there are, what kinds of edges there are? There are some edges that are already ended. That's not interesting. Amongst edges that are not ended, like their endpoint somewhere on the right, they can be the ones like beginning somewhere in the future, beginning somewhere inside of our segment, or beginning somewhere to the left of our segment. We should only draw edges to the ones that are beginning somewhere inside of our segment. So they're already in our stack, and they're exactly the ones that are to the right of our segment. So to draw all these edges, we should just find our position in the array, take all the segments in our array that are to the right, and draw edges to all of them. Sounds like it's slow, like we should, for example, find where we, but actually we can just go from the right and find our position, because the number of elements we will traverse is the number of edges we will draw, and if we are drawing more than n-1 edges, we should just say no, and that's all. So we can just draw all the edges, then we have to erase our segment, and it also can be done in time proportional to the number of edges we have drawn. We just move all the elements that were to the right of us one step to the left. Okay, we can delete all of this. Let's check that I didn't mess up again. Yeah, looks like. Yes, it shouldn't be very hard to check if we connected that. We could write DFS to check connectivity, but let's use this instead. Why? So we will have events. All the events have different coordinates. That's good. So it's starting and finishing. I will use one indexation. I don't usually do this, but like it's convenient if like there are two types of events with this ID, so we can say that there are positive and negative events. Initializing the issue. Now we don't really have to check if we have drawn too many edges. This will just check if the edge is inside the component. So if there is starting, we just add to our array to the end of it, and otherwise we have to draw some edges. So we find our position, and we have to move everything that was to the right of it, one step to the left, and also attach. So in problem E, we are given a tree and we have to generate the segments like in problem D, so that graph built on the segments are exactly the tree that we are given. I think this is really hard. But maybe the restaurant of the answer is not easy, but like the general idea. Like if the n was small, how to do it? you can just find any leaf in our tree, delete it, build the segments for graph with deleted leaf, and then how to add segment such that it has only one byte edge. Well, we just add the segment which endpoints are around one of the points of its parent. Then it's kind of obvious that there is an edge to parent and there are no other edges. Okay, let's do exactly that. We need a data structure that can store the elements in some order and find some fixed element and insert element to given position. This data structure called double linked list, and basically we are done. Yeah, I'm pretty sure that we can do all of this just by doing DFS. Okay, the number of nodes in our double linked list for vertex v will be 2v and 2v plus 1. And so to the right of node 1 will be node 1, to the left of node 1 will be node 0, and to the right of node 1 and to the left of node 0 there is nothing, so it's node 1. Cool. shouldn't need to use it. So if we are not at root, we should find one endpoint of the segment from our parent and insert our endpoints to the left and to the right of it. So we want to create node X and insert it to the left of node Y. So what should change? We want to look what are to the left of node Y now. If it's -1, then probably we will need some. But we shouldn't do some things. We shouldn't change anything for this node. I mean, we probably could. Yeah, this should pretty much work. Like we can create cycle actually with one special vertex. And I even think that it is kind of better. So let's do this. Yeah, with two special nodes, I think. And in this way, we shouldn't. No, this is yeah. Let's add a root in hands. So okay. To the right of, to the left of 0 will be 2 times n. To the right of 0 will be 1. To the left of 1 will be 0. To the right of 1 will be 2 times n, our special vertex. And then obviously to the left of 2 times n will be 1, and to the right of 2 times n will be 0, because 2 times n is to the left of 0, it means that to the right of 2 times n should be 0, and that's all. Then we shouldn't think about this. Yeah, it can be 2 times n, and it's fine. Cool. So we want to insert our new node X here. So to the left of it will be X, and to the right of it will be Y, and to the left of Y will be X, and to the right of Z will be also X. And we don't actually need this, because we can just, to insert to the right, we have to insert to the left of right neighbor vertex. Cool. Now we have to print the answer. This should be 2 times. To print the answer, we should just stand in 2 times n, our special vertex, and go to the right 2n times. And the answer of divided by 2 where v and 1 is, I think that's all. It's not the same. It would be funny if it were, but yeah, we have edge 2, 6. 6 is very small. We have edge 1, 2. We have edge 1, 3. We don't have edge 2, 3, it's fine. And we have both the edges 3, 4 and 3, 5, but 5 is inside 4. This is fine. It says something about permutations, but I don't think that's important. So we have n lengths. All of them together are independent, and in each event, look, we have so we have n variables. All of them are independent of each other, and the probability that and all of them are the same. So the probability is 1 divided by n, and otherwise 0. So it can be only 0 and 1, and the probability that it is 1 is 1 divided by n. And we want to find the expected value of the sum of all these things. power k, modular some number. It's good for 50, but I don't think this is probably about 50. So, and nm is big, and k is up to 5000. So it's probably should be solved in k square. So let's open all these brackets, multiply everything. We will have n to the case number of segments. Each segment is a product of some of these x's. Then by linearity of expectation, we can say that expected value of this thing is sum of expected value over all these things. Like basically, we want to look at all the strings of length k. String length k, and these are like the indices we choose in first, second, third, and so on case bracket. All of this good, and we should sum up over the expected value over all these strings. What is the expected value of this one product? Like we have basically if this string s, then this is s1, s2, sk. So each of these things are either 0 or 1, so if we multiply all of them, like every power of the same thing, like every positive integer power is the same as just taking the variable. So like this thing, let's say that I don't know what index to use. Let's say that pi is the number of j's such that sj is I. So it's the number of how many times we used this fixed variable. So expected value of x in power pi is just expected value of x if pi is at least 1. If it's 0, this expected value is 1. So when we look at this product, we can like group by the value of sj, and for each non-empty group, expected value group by sj. Then each group is independent from each other, so expected value of this thing is product of expected value of group, and for each non-empty group, expected value of this product, which is actually power, is just expected value of x, which is 1 over m. So the expected value for one such string is actually like the product over all non-empty groups of 1 over m. and this is actually 1 over m power g of s, where g is the number of non-empty groups. So actually this problem, like after some simplifications, this problem asks us to calculate the sum of these values over all strings of length k over alphabet of size n, where g is the number of different letters used in the string. Well, okay. We can see that the number of these like different summands is just the number of different values of g, and it's not more than k, because we have either 1, 2, 3 or k different letters used in the string. So if we will calculate the number of such strings for every j, then we will just calculate this value by just trying all the j's and adding to the answer this value multiplied by the number of strings with this number of j's. Cool. So how to calculate the number of strings with given number of different letters used? So it's actually not that hard. Let's at first say that we fix what G letters we will use. How many ways to fix this? Like it's obviously choose G from n. We have n letters and we only want G of them. But then we have to somehow fix that we only used this. We used at least one of every of each of these G letters. I guess, yeah, we could be doing some inclusion exclusion, but I think DP is actually easier. So we can calculate DP len g is it's just the number of strings of length n that use only g in different letters and use all of them at least once. How to do this? What can we do if we have such string? We can add some of the letters we already have. There are only j of them. So we can go to len plus 1. The number of different letters used is not changed, and we can choose one of G ways to do that. Or we can go to also add one letter, but one of the letters that we didn't use before. This way the number of used letters will increase. And in how many ways we can choose? Well, we had n letters and G of them are already used, so there are n minus G letters that we didn't use. And that's all. This dynamic programming can be calculated in square k times. this is utmost key and this is also utmost key. So we just calculate this the name problem. We don't need of k-square memory. We can just store the last two rows of last two columns of this dynamic programming, and when we calculate all of this, we just will sum up these things and we are done. And okay. We'll have to use inverse element once to calculate 1 over m. So I guess I had to write something to calculate inverse element. So for example, I can write binary exponentiation. I'm using because obviously we cannot use more than n different letters. I could say that it doesn't matter. Like we will multiply by 0 somewhere here, and we can just multiply up to k. Well, I guess that will be fine. I forgot to copy GP. Wow. Okay, fine. Some crazy, crazy stuff. Okay, I guess this ends my screencast. Thanks for watching.